We now discuss the optimization of surfaces. In the case of surfaces, we follow a procedure similar to what we do when we have y a function of a single variable x, as we've been doing until last year. However, this generalization involves some rather intricate calculations and formulae. You may recall we said that for a single function y equal to f of x, this was defined as a maximum point, that a point of minimum, and you got various other things like points of inflection, etc. And there were various properties of the first derivative and the second derivative that defined these things. For example, in all of these, the first derivative was equal to 0. So if this was y equal to f of x in any situation, at these x values, f dashed was equal to 0. Then, of course, the second derivative defined whether it was a maximum or a point of inflection. For example, if the first derivative was 0 and the second derivative was positive, we ended up with a point of a minimum. And if the first derivative was 0 and the second derivative was negative, we ended up with this situation here in which the point is a maximum turning point. In the case of the point of inflection, there was something a bit more involved in that the second derivative had to change sign as one went through the critical point. Okay. Another thing to keep in mind in optimization is you may not have a point, a single point that is a maximum or minimum, but rather you could also get a function along which the surface has a maximum or minimum turning situation. For example, you may recall we discussed the parabolic cylinder that looked approximately like so. Okay. In this case, the function that defines that whole line serves as a turning point, a set of turning points. So along every point on this line, you have a turning point, a minimum turning point. So it's a whole function that defines the minimality of the surface. So these situations may also arise. Okay, we will not go into the theory and the details. Rather, we'll just present some procedure for determining the maximum and other situations that may arise. So first of all, suppose we have z is a function of the two variables x and y. So we've got this scenario, x coming out of the page, y and z, i.e. the zy plane, are on the page itself. We define a discriminant to be equal to, and it's a discriminant that's going to arise relatively often, defined as the second derivative of z with respect to x multiplied by the second derivative, partial derivative, of z with respect to y minus the second derivative, i.e. first derivative with respect to x, second derivative with respect to y, derivative with respect to x and y squared. So we define this as the discriminant. And the signature of this discriminant is going to play an important role in deciding max and mins, etc. Okay, so in the first step, we discuss the first derivative with respect to x and y being equal to 0. So we solve the first derivative of the function with respect to x equal to 0 and the partial derivative of the function with respect to y equal to 0. At the points where this occurs, we look at the signs, the signatures of the discriminant. And I'll summarize the various scenarios that may occur. case number A, if the discriminant is negative, we get what is called a saddle point. So if the first derivative is 0, and if the discriminant is negative, we get a saddle point. And you remember what the saddle looked like in one example. If this is a saddle point, then on the page you may have the surface doing that, and at the same point you may have a perpendicular part of the surface coming out of the page doing that. So you can see it's again, this central point is a saddle point. So this arises when the first derivative is 0, and at that point the discriminant is negative. If the first derivative is 0 and the discriminant is positive, we have two further situations or possibilities. If in addition to the discriminant being positive after the first derivatives are 0, if the second derivative either with respect to x or y are positive, I should say this is or that are positive, then we have what is called a proper minimum. And in the second situation, if we get the second derivative with respect to x or with respect to y being negative, you get a proper max. So remember, in B2 we have first of all the first derivative equal to 0. The second point is that the discriminant be positive, and furthermore, if either the second derivative with respect to x or y is either positive or negative, in which case you get either a proper max or proper min. Scenario C in number 2, if the discriminant is 0, a whole lot of things may arise, but this is where we may get the surface having a series of points. In other words, a whole curve that defines either the max or min of the surface, very much like the parabolic cylinder. So this is where I'll say compare the parabolic cylinder, and you look at examples of this. Compare the parabolic cylinder that I discussed above. So you get a whole function along which the surface is a maximum or a minimum. How do we define max or min? Again, if the second derivatives are either positive or negative. Okay, we'll start off with a basic example. Examples 1. So suppose we have the function z given by the following product, which is 1/3 x cubed minus x multiplied by y squared minus y. So this one is nicely factored out. So what we have is the first derivative with respect to x. That means all the y's are constant. What we get is x squared minus 1, y squared minus 1. Y squared minus 1 is a constant. When you differentiate with respect to y, the first bracket is a constant. You differentiate the second bracket, which is derivative with respect to y, which gives us 2y. Right, so if we let zx equal to 0, it's clear that we have the following possibilities of x. Then we get x equal to plus or minus 1, or, coming from the second bracket, equal to 0, or y equal to plus or minus 1. So there's those possibilities. If we let the partial derivative of z with respect to y equal to 0, then again, putting that product equal to 0, it's clear that by putting 1/3 x cubed minus x equal to 0, we'll have x equal to 0, x equal to plus or minus the square root of 3. You can work that, check that out. And if you let y squared and 2y equal to 0, you'll get y equal to 0. So or from the second bracket equal to 0, you get y equal to 0. So let me just say that this comes from there, and this case comes from letting the first bracket equal to 0. And we have a similar situation in the previous case. Right, now we need to classify these. So in this case it is actually quite convenient to draw a little table. So if we have a little table that does this, in which we look at the possible scenarios. So suppose in this first case we have zx equal to 0, and on the vertical scale we classify zy is equal to 0. So when zx equals 0, x equals plus or minus 1, or y equals plus or minus 1. When zy equals 0, you may have x equal to 0, you may have x equal to plus or minus square root of 3, and we have one more possibility, in which case we have y equal to 0. It's clear you can't have values from x on the vertical scale or on the horizontal scale being paired off with values or x values say on the vertical scale. So you will not get this scenario or that scenario, and you can't get y values from the horizontal scale being paired off with y values on the vertical scale. So this is out. So the possibilities then are x equal to 0, y equal to plus minus 1, x equal to plus minus root 3 compared with y equal to plus or minus 1, and then x equal plus minus 1 paired off with y equal to 0 as possibilities. Right. We need to calculate the discriminant at this point, which requires the second derivatives with respect to everything. The second derivative of z with respect to x is the derivative of zx with respect to x, which is very clearly 2x into y squared minus 1. If you differentiate z with respect to x and then with respect to y, or vice versa, you get x cubed minus 1 multiplied by 2y. X cubed minus 1 multiplied by 2y. This you can do zx with respect to y or zy with respect to x. Incidentally, this is a little error. This little 3 should in fact be a 2. Right. Derivative of z with respect to y twice. This is clearly taking zy with respect to y. You get 2 times 1/3 x cubed minus x. And therefore, if you determine or constructed the discriminant, which I defined above in the formula, if you work all that out, you get 4x squared. Keep in mind 4x squared is always positive, multiplied by 1/3 of x squared minus x cubed minus 1. No, that's x squared minus, so it's okay, so that is 1/3 of x cubed minus 1. Let me just make sure that I've got my calculations correct. Zxx, zyy, if you multiply those two, you get 4x into y squared minus 1 into 1/3 x cubed minus x. One-third x cubed that writing is not good. So let's fix that up. That's 1/3 x cubed minus x into y squared minus 1. And then squaring of zxy, you get x squared minus 1 all squared. The 2y squared gives us 4y squared, so I'll put this in front. X squared minus 1 all squared. There's a bit of an error here. Let me just make sure about the first term in this delta. If I removed a common factor, what I would have got, so let me fix that up. This would actually be a 2, and this would be a 1. So let's see, that is x squared minus 1. There we are, that should make it correct. Okay, so that's delta. Now these critical values from this table, i.e. from that table, have now to be, sorry for that, we now have to substitute that into, what am I doing? That's what I'm meant to do. We need to substitute that into the discriminant. Right, let's do this piece by piece. First of all, at the points with coordinates x equal to 0, y equal to plus or minus 1, we'll deal with this simultaneously. It's clear that the discriminant is going to be equal to, well, if you put x equal to 0, the first term is going to be 0, the second term is going to be minus 4 times 0 also, that's multiplication there, so that that's going to be equal to 0. I'm sure this is not correct. Let me just check this thing. If you okay, hang on. If I put x equal to 0, then this will be minus 1 squared. This is squared there, so this is going to be some positive number. So this is going to be 1 for the y squared, and then this is going to be minus 1 all squared. If you work that out, this is negative. Okay, that's what we get. So what we have are saddle points. So at the points with x coordinate 0, y equal to plus or minus 1, first derivative 0, the delta, the discriminant, is negative, so you get saddle points. Right. Now at the points with coordinates x equal to plus or minus root 3 and y coordinate plus or minus 1, we can deal with this simultaneously. We get the delta is equal to, well, it's clear that if you put x equal to, rather y equal to plus or minus 1 into that term there, that will be equal to 0. So the delta from the first term, rather, let's put it in black, is going to be 0. And then in the second case, if you put these x and y values, it's certain that this is going to be minus 4 times some positive number. So we get this is 2 squared. If you work that delta out, this is clearly negative. So here too, we get saddles. In fact, I should say there it's plural, and here it's plural too. So we got another 4 points defining saddles. And now we'll take the point 1, 0 at 1, 0, that is x equal to 1, y equal to 0. Let's do it together, plus or minus 1 together, as we did before. Save us some work. So I'm going to say plus or minus 1, 0. What is delta then? Well, if you put x equal to plus or minus 1, the first term is going to be positive. So let's just evaluate the first term. So if you put x equal to plus or minus 1, you get 4x squared, which is 4. then if you put x equal to plus or minus 1 into a third squared minus 1, you're going to get minus 2/3. You can check that. Minus 2/3, which is 2/3. And if you put y equal to 0, this is going to be minus 1. And if you look at, again, the second term in the discriminant, which is that term there, if you put y equal to 0, that's going to be 0. This is in fact positive. So here you have max or min. And the max or min is going to be defined by what the sign of the second derivative is. Why am I doing that? That's what I meant to do. Okay, so here we have to take these 2 points separately. So if we take the point with coordinates 1, 0, we need to see what's the sign of the second derivative. It's clear that the second derivative, if you just go back and see what z double x is, this is going to be equal to 2 times minus 1, so this is negative, and if your second derivative is negative, what you get is a proper maximum, right? And at the point with coordinates minus 1, 0, a further analysis, we get here the second derivative with respect to x is equal to 2 times minus 1 times minus 1. This is positive, so therefore here you get a proper minimum. So that's then all the points classified in this example. We will look at a similar example. Sounds like a practical example, but it's really, the calculations are straightforward. So in this case, what we need is to find the dimensions. So find the dimensions of a rectangular box. It's a box, sorry for the writing, of a rectangular box lying in the first octant. That is the equivalent, in other words, where x, y, z are all positive, lying in the first octant. Octant coming from 8 sections. The first of these 8 sections in which x, y, and z are both positive. In the first octant, let's sketch this thing. So here's the x-axis, here's the y-axis, and let's z-axis. So this is a rectangular box that is of this shape. Okay, and it does that. There's the rectangular box in the first octant where x, y, and z are both positive, right? Find the dimensions of the rectangular that with maximum volume. So we want to maximize the volume. With maximum volume, right? If one of its corners, it's clear which vertex it will be, if one of its vertices lies on a plane, vertices lies on a plane, and the equation of the plane here is 6x plus 3y plus 2z equals 18. So it's clear that it is going to be this vertex here that lies on the plane with that equation there. Now let's suppose the general value there is x, this is a general value y, and this is the general value z, right? So then it's clear that the volume will be equal to length times breadth times height. The length is x perhaps, the breadth is y, and the height of this box is z. We want to maximize this function. To maximize this function, we need to rewrite this function in terms of just two variables. So we need to replace the x, y, or z. What we will do is we'll replace the z. So since one of the points lies on a plane, and the plane is, of course, that, we'll solve for z in this equation and substitute it into the form of the volume. So from that, it's clear that the z coordinate, if we solve for, can very easily be obtained to be 9 minus 3x minus 3 halves of y, so that the volume, therefore, let's call it v, will be x times y. Solve for z, you get 9 minus 3x minus 3 halves of y. So now we have clearly a function, the volume being a function of just two variables. It might be convenient to multiply all of that out when we're doing the derivatives. So we get minus 3x squared y, and then lastly minus 3 halves of xy squared. So this is the function we want to maximize. So this is the function on which we do our calculus. So from this we get therefore Vx and Vy. Clearly this is going to be straightforward. This is going to be 9y minus 6xy minus 3 halves of y squared. If you differentiate v with respect to y, you get 9x minus 3x squared minus 3xy. At some point we're going to need, maybe I should put that in a different color for now, v double x. Differentiate the volume twice with respect to x, you get minus 6y. If you differentiate v twice with respect to y, you get something given by 9 minus 6x minus 3y. And if you differentiate v with respect to x and y, you will get, wait a minute, this should have been, let me just change that. This in fact should be vxy. So let me rectify that. So that should be vxy. And vyy is very simply minus 3x. If you calculate the discriminant, it's very easy to show that the discriminant, which is defined as vxx vyy minus vxy squared, will be given by or maybe I should leave it for now. This is minus 6y minus 3x minus the vxy squared, which is 9 minus 6x minus 3y. So these are the formulae we're going to need. I'm not going to do the complete example, but we can show that Vx equal to 0, Vy equal to 0 simultaneously will produce the following results. Maybe I should do the calculations. Well, let's do it. Let's erase this. Vx equal to 0 Vx equal to 0 implies the following. So from above, if you put Vx equal to 0, we get y equals 0, or y equals 6 minus 4x. If you put Vy equal to 0, we get x equal to 0, or y equal to 3 minus x. You can clearly show that. Then, of course, you cannot take both x and y equal to 0. So this is not possible. Why? Because if you put x and y equal to 0, the volume will be equal to 0. So that solution will be rejected. So we'll solve for these two simultaneously. If you solve for that simultaneously, put y equal to minus 3x, y equal to 6 minus 4x, and so on and so on. What we end up with is x equal to 1, y equal to 2. So this implies x equal to 1. If you do this simultaneously, y equals 2. We need to put this into the discriminant. We can show that for these values of x and y, so at the point 1, 2, we get that the discriminant very easily can be shown to be 27, and that is positive. So what we end up with here is a proper maximum. Clearly, if you go back to the y in terms of the z in terms of x and y, we can show from above that at the point with x equal to 1, y equal to 2, the z coordinate can be shown to be 3. So therefore, the maximum volume will be at the point, before I calculate the volume, I should say the maximum, therefore maximum volume at the point with coordinates 1, 2, 3. So the box will have dimensions x equal to 1, y equal to 2, z equal to 3. If you want to calculate the volume is x times y times z, and the maximum volume is at these values x times y times z, 1 times 2 times 3, which is equal to 6 in some cubic units.